scenarios and seeing how it affects the BECCS system overall, and we'll focus in the US. So when you look at the US, there are two main databases that can supply you with biomass supply. One is the NREL Biopower Atlas. That's more of a look at current day biomass resources in the US. And then you have the Department of Energy's billion-ton study. And that gives you more of an outlook into the future, looking at the technical potential of biomass supply into the future. In these databases, you'll find 5 main categories of resources. You'll find agricultural crop residues, forest residues, mill residues, urban wood wastes, and dedicated energy crops. In addition, you'll find that these databases have varying degrees of constraints on the biomass supply. The 2 main constraints that you'll find are additionality constraints. This often constrains the biomass supplies to biomass that is currently not being utilized by other bioenergy applications or other types of recycling applications that sequester the carbon in the biomass already. And then you have the sustainability constraints, which limit how much harvesting of biomass you can take from a lot of these residue systems in order to avoid a lot of the soil degradation concerns that arise. And so out of these 5 categories, most of the concern that has come out in the last decade or 5 years or so have been really aimed at dedicated energy crops. Again, primarily this is an issue of scale. When you start looking at the cropland that is being suggested to be allocated for dedicated energy crops, you'll find that depending on the scenario, somewhere up to 700 million hectares by 2050 is sometimes allocated to dedicated energy crops, sometimes up to 1.5 billion hectares. To put that in comparison, current day global agricultural land area is around 1.5 billion hectares, give or take, and primary forest is around 700 million hectares. And this issue really starts being put into context when you start talking about the cropland requirements for food production in the future. Estimates for extra cropland necessary to meet future food demand are also around 500 to 700 million hectares. Then you look at the underlying assumptions in these databases and you'll find annual crop yield increases that range from 1 to 4%. If you look at the last 50 years, you'll find annual crop yield increases that are around 1 to 2%, but it's uncertain that those yield increases will continue and definitely uncertain whether they'll reach 4%. You have studies coming out about the emissions, the life cycle emissions of energy crops, and then given how much biomass that we have in the future, it'll likely be segmented between different types of bioenergy applications. Not all of it is going to be funneled straight into BECCS. And all of that is not to say that we shouldn't pursue dedicated energy crop growth. The only thing that the message that really we want to show with this study is that these databases are really kind of a best case technical potential of future biomass supply. They are not projections of what biomass supply will be in the future. Will they be this optimistic in the future? Maybe. But if they're not, you know, what's that impact on both BECCS deployment and negative emission potential estimates? And when you look at previous negative emission potential estimates, when we're looking at energy systems and these techno-economic optimization models, you'll find that the underlying databases are heavily reliant on these ambitious biomass supply. So in the we have 2 main studies in the US that did optimization of BECCS and estimates of negative emission potential. You have Dan Sanchez, Nature's climate change paper, and then you have the recent PNAS study. And you'll find in the climate change paper, the underlying biomass has really inconsistent constraints for the various different types of biomass supplies. And when looking at the PNAS study, you'll find that some of the scenarios heavily rely on dedicated energy crops that aren't developed yet. This is not to say that these studies in any way are bad or use bad methodology, but they represent the upper bound of what is possible in terms of BECCS deployment and negative emission potential. With this study, we want to start asking, what are some of the lower bounds of these estimates? So the goal of the study was to construct these somewhat crude biomass supply scenarios and then use them in a techno-economic optimization model to see how they impact the development of BECCS supply chain and how they impact the total negative emission calculations that we get. So these are the 5 scenarios that we came up with. The first is economic supply. This is taking all of the biomass that's available below $60 a ton. In the second scenario, we add these additionality constraints. This mostly limits mill residues and the municipal solid wastes present in the US. For the third scenario, we add sustainability constraints. This significantly reduces the amount of residues that are available for bioenergy applications. This third scenario, you'll find most agrees with the billion ton study. Then the fourth and fifth scenarios kind of crudely cut the dedicated energy crops, which is DEC, in half. And then for another one, we've completely removed them from consideration. And you might, again, think that the first 2 scenarios are unreasonable because sometimes additionality or sustainability constraints seem somewhat intuitive, but when you look at the underlying biomass of some of these studies, you'll find that they're not consistent. As a first pass, we kind of used these biomass resources and just multiplied conversion factors using their energy content and a kind of stereotypical future BECCS power plant with efficiencies to see how much energy we could get out. Generally, what you'll find is that none of the scenarios have enough energy content in a BECCS power plant to meet the same electricity production that coal power plants did in 2014. But some of the scenarios definitely come close, but you'll also see that the scenarios have a large impact on how much you can get. And this is how the maps end up looking like. Most of the upcoming dedicated energy crops are to be grown in kind of the southern plains regions in the US. And this is important because there's a lot of storage reservoirs in the southern US, especially above the Gulf. There's a lot of space to put CO2 into geologic reservoirs. So we took these biomass supply scenarios and then we applied them to a geographically explicit multi-integer linear programming optimization model, BEWARE. This allows us to consider a wide range of technologies, and along them we consider a bunch of cost parameters and emission parameters. What we used as our power plants to either retrofit or replace was the coal fleet in 2014. This is publicly available data from the EPA. So we have about 633 power plants, make up around 470 gigawatts of capacity, and in 2014 emitted about 1.7 gigatons of CO2. And then we use our biomass supply scenarios and the USGS geologic reservoir data for the US. In the spatial optimization model, we have various technologies that these coal power plants can either be retrofitted with or completely converted into. So for retrofits, we have our CCS, post-combustion retrofits. We have direct co-firing, indirect co-firing. And then for conversion, demolition and rebuilding a new power plant, we have bioenergy plants, new BECCS plants, and new fossil CCS plants, where you would get increase in efficiency in the power plants. You'll see that we model both where we biomass harvest from and the transportation by truck. And then we also model the development of pipelines and where we would store the CO2 in geologic reservoirs with injection constraints and geomechanical injection constraints as well. All of these have emission factors associated with them and cost factors associated with them. So let's start looking at the results. The way we did it is we constrained the emissions of the entire system from 0 to 100. So at the end, we have on net, we have 0 emissions, but we do have positive and negative emissions in the system. In the first figure, you'll see total generation. Going down, you'll see total capacity. Here in green, you'll have BECCS. In red, you'll have fossil CCS, and then you'll have a bit of co-firing, which isn't developed that much. In the top right, you'll see that we have the amount of injection on aggregate in the entire system, in green being negative emissions, biomass emissions that are being injected, and in the yellow, we have the fossil emissions that are being injected. And then our last figure, we have biomass use. I'm sorry the numbers are kind of small, but in general, you can see the different trends that are occurring, and you'll see the comparison between the scenarios. You'll see that biomass use increases until it plateaus. Usually we reach about 80 to 90% utilization of all the biomass that we have in our scenarios. And as it's rising, you'll see BECCS deployment also increase. As soon as biomass is all utilized, all the further emissions after that are reduced through fossil CCS. And because fossil CCS doesn't have a negative emission factor associated with it, you kind of need a disproportionate amount more of fossil CCS for the same emission reduction target if you take out some BECCS. So now we look at the scenario where we don't have any dedicated energy crops, and what you'll find is that biomass, as one would expect, is completely utilized a lot earlier on in the optimization models, or at lower emission reduction constraints. With that, you get a substantial increase in fossil CCS deployment, which is in red, and with that occurs a lot more total sequestered emissions, which is the summation of the green and yellow in the top right. So you look at 2040, very similar results, except they're a little bit even more extreme. This is because the proportion of biomass that is coming from dedicated energy crops is a lot higher. Just to put kind of some very crude and averaged, numbers over the entire system, at the 100% emission reduction, you'll see that levelized cost of the system, which is the blue line in the first figure of the scenarios, increases about 43% if you take out the dedicated energy crops. BECCS deployment decreases by 53%, which leads to a decrease in possible negative emissions of about 57%. Looking at the spatial deployment of BECCS in these two scenarios, you'll see that, again, a lot of the difference is in the southern plains. So in the southern plains, again, we lose a lot of storage potential, and because of that, it's just a lot of potential that could have been there if dedicated energy crops were to be developed. And so you'll see the differences. We have about 70 gigawatts of BECCS capacity in the high DEC scenario, and only 35 in the low DEC. And we'll see this cut of about half of the emissions, negative emissions that are possible, from 750 megatons down to about 300 megatons of CO2. These are annual negative emissions. Comparing this to what is necessary in the integrated assessment models, by 2050, it seems that the US would require about a gigaton of CO2 negative emissions in 2050. And so you'd see that the development of these dedicated energy crops is really essential to meeting these negative emissions targets in the integrated assessment models. And so lastly, just to kind of sum things up, these negative emission potential estimates in these energy systems are highly sensitive to the underlying biomass supply. When you look at the underlying biomass supply of previous studies, it's clear that accepted constraints are not there, and they heavily rely on dedicated energy crops, which are increasingly being criticized. Removing it removes about half of the potential, and so the message is really, it's not that we shouldn't develop these resources, and it's not that we shouldn't develop BECCS, but more that before all the studies are giving these upper bounds, and we need to be careful not to overestimate the tools that policymakers have, because when we show these studies and we have a number that says, say, in 2040, we have this amount of negative emissions, policymakers will take that and use it as a tool in their their policy scenario decision making. And so that's it. I just want to thank the YASA team very much. If you want to check out more about the BeWare model, there's a link. Thank you.